we are trying to compute parity, right, and see the definition of Turing machine in action. So read a bit of X. Basically, it's a incremental algorithm. Roughly the Turing machine proceeds incrementally. So it will read bit by bit. So say you have read the first I bits. When you read the I plus 1th bit, either it will be 0 or 1. So if it is 0, you don't change your current parity, leave it unchanged, or you read 1 and then you flip the parity, current parity, right? That's the correct thing to do, because remember 1 plus 1 is 0, while 1 plus 0 is 1. Right? So when you see a 1, you have to flip. When you see a 0, then you don't flip. Okay. Third step is continue till you reach the blank cell in the input tape. So continue till input cell becomes blank. Blank means that the input is over. So you keep repeating this loop. It's just a simple loop, and the head keeps on moving forward on the input tape, and the states are only 2 more. So obviously start finish is there, but you also have you can think of as parity 0 state, even state, odd state, right? So and then whatever state you are in when the Turing machine halts, that's the answer. So write 0 or 1 as the output based on the state. On the current state, and then move to finish. Right, so that is how the Turing machine would scan the tapes and change the state. Right, so very simple algorithms you can see are clearly implementable, simulable by a Turing machine. And in fact, we can also draw this as a picture. So you have the start state and you have the finish state as 2 vertices, and you have, let's say, the even state and the odd state as vertices. Now think of the vertices as the states and edges as transition function values. So when would the transition function say that move from state QS to Q even? Q even corresponds to current parity 0, right? So if you see a 0, let's say the first 0, then you move to Q even. Or even in this case, so you are on the start configuration, and from there you will move to you will not change the cells, each of them will remain start symbols, but on the input you will move right. Don't move on the work tape, right? So the only information here is actually R, this right movement on the input tape. And the other information is that after start you have moved to the parity 0 state, and now when you move on the right, now the input head sees the first bit, right? Based on that bit it has to take an action. So what is the action? So if this bit is 0, then don't change anything, just keep moving right. So read the second bit. State doesn't change because 0 means parity still is 0. On the other hand, if you see 1, right, then keep moving right. That's fine, but the state has to now flip, so it goes to odd, because first bit being 1 means parity has now become 1. Now in odd, if you are in odd state at some point of time, then again looking at 0 you will remain in the odd state, and you keep moving right on the input tape because you want to move to the next bit, input bit, right? And it seems that the work tape is not of any use. Work tape, the head is always on the start symbol, right? So this doesn't even need the work tape actually. And yeah, the reverse, if you see a 1. If you see a 1, then from odd you go to even. So this is kind of the loop, even to odd, odd to even, even to odd. Whenever you see 1, if you keep seeing 1, you keep moving in this loop. If you keep seeing 0, then you are at the same state, so even to even or odd to odd. And when will everything come to an end? When will you reach the finish state? So that is when you see blank. So at that blank, if you are at even state, then at that blank you write the output 0. And there is no need to move right anymore. A similar idea when you are at odd, you write 1. Okay, so this is the state diagram of the Turing machine. So above is the steps in words, and below is the state diagram, which is telling you in a compact picture. It tells you what the transition function is via the edges, what the states are via the vertices, and you can dry run the whole execution of your algorithm. So this is the state diagram. Okay, so you can see that even in a simple algorithm, almost a trivial algorithm, it takes a while to write down describe the Turing machine and describe the computation. Okay, so although the definition is easy, there is a lot of notation So it gets quite tedious to describe the Turing machine, but still you have to keep this in mind, because this is how everything is formalized. Every algorithm ultimately looks like this. Okay. So the state diagram describes the transition function, describes delta, with the nodes being states q, and the edges specify a transition. Okay, so nodes are states, edges are transition. States, you will see these big vertices, but the rest of the information you will see on the edges. And in this example, you can see that work tape was not used, and also you can see that the output is written at the last bit, at the end of the input tape. So in the example, work tape wasn't used, and output bit output bit is at the end of input tape. Right, this we saw in the state diagram, that when the transition happens from Q even to QF, we wrote 0 at the first blank you saw. So that is the end of the input tape, and analogous thing for Q odd to QF transition. So one property that you can see is that the size of the state diagram what does it signify practically? Right, a bigger state diagram means what? So bigger state diagram means a bigger program, right? So size of the state diagram is kind of proportional to size of the C program, let's say, simulating this algorithm. Right, that is the kind of the physical interpretation, if you will, of the state diagram. Bigger state diagram means that your C program will be that much bigger, because in the C program you have to take care of these steps. It's kind of a flow chart that you are implementing in the C program. So if there are more states, then you have to maintain more variables in your C program, and if there are more edges, then you have to implement more if then else conditions. Okay, there will be more loops, so for or while loops. So yeah, the program is fixed irrespective of how long the input is. right? That's an important thing to remember. This size is independent of right. So, once you have written the program, C program, it does not matter what the input is, or uh, your input can be arbitrarily large. So, in the future when there will be a bigger computer, bigger hard disk, you can the same program can run with bigger inputs, right. So this is something that you have to appreciate at this point, that the finite control and the state diagram, transition function, these things can handle any, I mean you have to design them so that they can handle any length input. Okay, so X can be infinitely arbitrarily long, so this is why you need the tape to be infinite. Although the program, the control is finite. Okay, so that was a quick recap of things you learn in theory of computation. And now let us get down to counting the resources, bounding them. So we start with time complexity. Of a Turing machine. So let F from strings to themselves, F be a function from strings to strings, and M be a Turing machine computing F. Let T be a function okay. So F is what you want to compute, you compute it by Turing machine M, and T is the function that I will use to denote time complexity. So what is that? So we say that M computes F in Tn time if for all input strings X M halts after at most T of X, T length of X. So this bar notation means length of X, how many bits there are in X, in T of X steps. Obviously just halting is not enough, it should also give the correct answer. So and outputs F of X. So it should halt and it should give the correct output in number of steps, a function of this function T of the length. Okay, so this is important. We want to capture time complexity as a function of the input string. Why is that? Well, because the input string can be arbitrarily long. So we cannot keep track of for which string how much time it will take. Okay, there are just infinitely many strings. So we actually want to focus on, we want to get a ballpark idea, a ballpark number, in this case function T, which tells you okay how good or bad the Turing machine is. So we have defined m computes f in Tn time. Similarly, you can define that what is the meaning of the expression m computes f in S of n space. Okay, so this phrase m computes f in S of n space, this will be how many work tape cells were utilized. So for example, in the previous example of parity computation, work tape was not used at all. Only one bit of the input tape was used, so it was actually constant complexity, space complexity. And what was the time complexity of parity computation? So the time that it took was proportional to the length of the input, right? So we can write that so for parity we saw that T of n was, time was around n. Okay, the length of x, that many steps there were, and the space complexity was just one. Right? No work tape cell was used, and one output bit was written. So that is what happened in this example Turing machine. Okay, now we also don't want to be too precise with T and S functions. We want to again get a ballpark estimate for these functions. For that we will formalize asymptotics. So what is asymptotic notation? So let f, g be functions. I'll shorten function to fn. Okay, so f, g be functions from natural numbers to positive reals or non-negative reals. So big O notation is like this. Okay, writing f equal to big O of g. What does this mean? Roughly this means that f is less than equal to g, but up to constant multiple. So if there exist constants c n0 such that for all n greater than equal to n0, f is less than equal to, sorry, f of n is less than equal to c times g of n. So note that there are two relaxations here. First is that f can be a multiple of g, but it has to be constant c. Second relaxation is that this inequality may start to hold after a while. Okay, this n up to n0 it may not hold. Remember that, but beyond n0 it's always true, right? So after a while f is bounded by g up to a constant c. This is what f equal to big O means. Big omega so big, if you write f equal to big omega, that's basically the opposite of first line. So you will write this if G is equal to big O of f. Okay, so if G is big O of f, basically this you are saying that f is greater than or equal to G up to a constant C. Okay. So big O is an upper bound, big O, omega is a lower bound. Then there is theta, f equal to theta G, which is if both of them are true. So you have both upper and lower bounds. Okay, G is less than or equal to some constant times f is less than or equal to some constant times G. So f and G are practically the same. That is what theta is saying. So theta is a good bound. Okay, ideally you want theta. You want this relationship that two things are equal. For big O there is a small o. What is that? So small o is this idea that f is strictly smaller than G. So it's not constant multiple, but I mean this is like saying so in the big O case f by G was like a constant. In small o case f by G is like 0. Okay, f by G tends to 0. That's a simple way to put it. As n tends to infinity, f by G, G becomes much larger than f and keeps becoming larger and larger, so the ratio is 0. Similarly, small omega, so small omega is opposite of this. So if G is small o of f, right? So instead of I mean small o is saying that f is significantly smaller than G, small omega is saying that f is significantly larger than G. And finally there is also an O tilde. What's that? So f is O tilde G if this is like big O, but here the constant multiple is relaxed. It is relaxed to smaller functions of G. So if f is less than or equal to G times some smaller function, so we pick log G. Okay, so G log G is written as O tilde G, or you may even allow constant powers. Okay, so log G is much smaller than G and we are just allowing constant powers of that. So you don't expect this to be too large. Okay, so although f could be larger than G, it is not much larger. That's the point. And just symmetric to this, you can have omega tilde so you write omega tilde G if G is if g is less than equal to, sorry, if g is equal to big O tilde f. Okay, so and so on. You can define such functions. This is the idea of all these functions is the same, which is understand the asymptotics of, let's say, time complexity. Okay, so if you are solving a problem by one Turing machine that takes f time, other Turing machine, other algorithm takes g time. How do you compare the goodness of these two algorithms? So you basically will use an algorithm that has a smaller time complexity, right? So you will want f equal to small o of g. That algorithm will be better for you because f time complexity is much smaller than g for larger inputs. And if f is equal to theta g, then you will not care much, although in practice the constants may be important. But in theory, f equal to theta g means that it's only a constant difference. So time complexity is kind of the same. So mathematically the algorithms are kind of the same. So this is the asymptotics we use, and we can see some examples next time.